With each passing generation of wireless networks, we are increasingly reliant on them for everything, ranging from consumer apps to a mobile workforce to IoT. The current move to 5G will only accelerate the indispensable nature of wireless. But for wireless service providers, the investment required is enormous, and careful attention to how customers are using the network, how satisfied they are, how to attract and retain customers, will make or break their returns on these investments. Getting the right data from the networks and subscribers to make real-time decisions will shape business agility and profitability. Some of the most critical data to understanding the health of wireless infrastructure and its profitability can be found in the edge data collected by the network itself. In this demonstration of Actian Avalanche, we look at edge-to-cloud data extraction and analysis for the purposes of wireless network fraud detection. So let's take a look at how the Avalanche hybrid cloud data warehouse can be used to detect fraud in the telecommunications space, specifically across the wireless network. Note the same principles could be used for wireLAN, cable, or other services where points of service delivery are easily defined by GPS coordinates mapped to network endpoints. We've configured Avalanche to deliver query results to Tableau for visualization. We could have used Looker, Qlik, Microsoft Power BI, or MicroStrategy, since Avalanche has connectors for all of these as well. Here we've switched from the Avalanche console to Tableau, so we can see a map of the US overlaid with the data from the cellular network. The data in Avalanche is real-world data we receive from one of our wireless service provider customers. It's known as PCMD, or per call measurement data. We've created a custom query that's used to look for cellular phone number cloning, a trick that allows a thief to make calls and bill them to an unsuspecting number. As we see here from this map of the United States, there are two phones making calls with the same number, but from different locations, and we suspect that one of them is fraudulent. Why? There are several calls made in the Arizona area during the same time frame as a call made from Hawaii. In fact, it would be impossible to fly from Arizona to Hawaii over this interval, so this is clearly fraud. You can see a line we've drawn between them on the map to visualize the difference. Let's look at a second example here. We have two red dots in the New York metropolitan area. Let's enlarge this so you can see it better. Two calls have been made at locations that are 5 miles apart with a time difference of 10 seconds. Although this is a far shorter distance than the Hawaii to Arizona case above, the time between the calls placed is still faster than a plane can fly. So it's not even someone violating air flight rules and talking while taking off and landing. In other words, this too is fraudulent. As a side note, you can also see the information for these two calls just above the map. We can also look at the custom query used on the PCMD, as you can see the window I've just pulled up. I'll explain more on this in a separate window, where it's easier to read the code because of the syntax highlighting. When we refresh the data source here, it executes the query again, and it's sent to the map. As you can see, it's extremely fast, almost instantaneously refreshing the map. Now let's switch back to the console again. Click on the Avalanche Data Warehouse cluster we're using for this demonstration. We have separate demonstrations that delve into the capabilities of our Avalanche Hybrid Cloud Data Warehouse, and we encourage you to look at them as well. And as you can see, we have several data warehouses running on Microsoft Azure's public cloud platform. Avalanche also supports AWS, Google Cloud, and on-premise and virtual private cloud deployments as well. Let's click on the one we've just started with. You can start and stop your cloud data warehouse, so you only pay for what you use and never pay for compute power you're not using. After clicking on the data warehouse we're using from the main page, we've moved to a detailed page that shows we have an 8 AU cluster, or 8 Avalanche units. You can scale dynamically up and down these AUs from 8 AUs to 128 AUs, depending on how much compute power you need. There's another factor aiding your pay for what level of control you use for your computer, while leaving your data and base payments against how much data you've stored in the data lake, in this case, Azure ADLS. For example, we've stored our PCMD data here as a large fact table consisting of 1 billion rows, further broken down into dimension tables containing tower information and the events we'll use as data for our fraud detection queries. Now let's open a query. We're opening in a separate editor in a separate browser window. In this query editor, you can interactively type your queries and save them, or alternatively, open and edit previously stored queries. This customized query can then be run and the results displayed in a Tableau dashboard. Let's run to Hawaii, Arizona's fraud query on a large fact table for the 1 billion rows to isolate calls from our suspected fraudulent phone number. To do this, we take the 1 billion rows and do an inner join on itself, easily performing a query in comparison logic on 1 billion rows times 1 billion rows, an extremely large calculation in the terabytes of data. To run a query efficiently, we employ key factors within the table, checking for different towers that are used, and most importantly, calculating the time difference and the distance logged in the PCMD data. These return values for the selected phone number are then run through a square root expression. Note, there are more elegant ways to do this, and we'll show you one of them later in this demonstration. For now, let's use the distance and time difference calculations to estimate velocity. We can then use this velocity to determine whether a single physical phone is either at a fixed position or moving over time. In this case, the velocity is greater than 150 meters per second, or at least 3 times as fast as a car moving down the German Autobahn. Not quite faster than a speeding bullet, but just as fictional as Superman flying through the air. And then here, this query does a union on a similar branch using Tableau and the Tableau connector. We'll show you a shorter form of this later in the demo. For now, let's go ahead and run this query that's highlighted or marked here. You can see it running and quickly completing with results displaying 14 rows, 2 rows at 4 locations that when plotted as the red dots linked Hawaii and Arizona on the dashboard, and the other 12 rows to dots that link with implausible locations over time, locally in Phoenix, Arizona. Here's another view of the sample PCMD in a record format, including the call start time, call lists, whether it's a data connection or a voice call, the phone number and the IMEI numbers, and so forth. In the yellow column, here we see the event ID, where 11 constitutes a normal call. Other event ID values reflect other network and call conditions. In fact, if we switch to this event table, we can look up what each event value maps to as a condition. Again, 11 for normal calls. But for example, here we have the condition ID for core network blocks. And here we have tower information keys that refer to towers or the beginning of the call. And here for the end of the call and the last hour sequence number. And here you see latitude and longitude information that's used for calculation and visualization on our Tableau map. Now let's start another query editor from the console. You can see verification we have 1 billion rows in our fact table here. And there is also the view used that allows us to easily switch between different sized data sets. And here it's set to the 1 billion row fact table. Earlier, we said we'd look at a more compact query where the union doesn't occur. In Tableau, it uses a common table expression. And then we select the query, and then it lists the results here in a union to get these 2 rows here that constitute the endpoints of a line between the 2 different geolocations, from one location to the other, associated with where a potentially fraudulent call has been made. Another thing you see here, or you might have wondered about, is this square root expression. The purpose of it was described above. Now, let's look at a more elegant way to execute the fraud calculations by employing user-defined functions, or UDFs, that are available within Avalanche. User-defined functions help to parse complex queries into small segments, more understandable and easier to maintain and debug. For now, let's just show how it works. We can run it here on the server in our SQL command line tool. It's the same query we ran before, but this time with the UDF the distance instead of a more complex square root calculation. Instead, it's embedded here in the UDF. And I can execute this UDF, and now we see it completed in 2 seconds. Now let's get back to this Tableau query. As I said before, with this dataset, some calls are blocked by the core network, and filtering out all the event ID return values outside of 11 would restrict us to querying for successful calls only. You can see here we're checking for event ID 11. So let's run this query again with the event ID 11 qualifier. And now only one call is left, and we see the remaining single phone number here has a time difference of 10 seconds, mapped as the red dot on the Tableau map that you see here. Let's copy this and quickly go over to Tableau. Click on the data source, open the custom query editor, and we replace that query here. And now switch on the map. So it focuses now on the one occurrence, filtered by event ID 11. And we see here that the distance is about 5 miles, and the time difference is 10 seconds. No plane is that fast. The PCMD dataset we used here could of course be used for a wide range of use cases. In the interest of clearly bringing to light how Avalanche can be used, we selected this fraud detection case. However, there are a myriad of cases, and the key performance indicators, or KPIs you see here, provide tracking results for using various elements of this fact table dataset to understand how well service provider operations are going. You can see they're grayed out, but we can execute them to refresh. And these 6 KPIs should look very familiar. If you've worked in the telco space, we have the load as the total tonnage and kilobytes connection attempts, connection failures, and successful connections. And you can see we've used these KPIs to build a dashboard with the relevant information for the service provider operator. And here we see that the queries are executed in the background. And you can look at the detailed data. Drill down to see connection drops and successes, and you can see and do additional analysis. And again, here we see the query executed. You can easily build sophisticated dashboards. But what really counts is the ability to refresh large sets of data interactively in real time. In summary, with Actian Avalanche Hybrid Cloud Data Warehouse, you get blazing fast performance out of the box that allows you to easily ingest data from back-end ERP and operations management systems, as well as data from the network's edge, such as PCMD data we've shown here. You can use this to perform complex queries that can provide the right insights to rapidly detect fraud. For more on Actian Avalanche Hybrid Cloud Data Warehouse, or to get started with a live demo or free trial today, visit actian.com/avalanche.